Well, my name is Ismael Ripoll, and Hector Marco is my colleague. We're going to talk about ASLR, the weaknesses several weaknesses, general weaknesses in the design and implementation of Linux and PAX ASLR. And okay, we will show you, let's see if this can go quickly. Okay, I will give you a brief, fast, quick overview of what is ASLR. I will show you the weaknesses, also a tool that we have developed in order to find the weaknesses and to develop a new version. Okay, because a brief explanation about how one of the weaknesses, the correlative weakness, can be exploited. And this has been presented by my colleague, Hector Marco. And we don't like also to show the bugs or the vulnerabilities, but also give some hope that there are solutions to them. Okay, so we have developed ASLR next generation, which is a new version of ASLR, which maybe will replace the existing one in somewhere, sometime. Okay, so the background, I'm going to present it. ASLR is not a removal of bugs, but is a prevention of exploiting bugs. Okay, so rather than removing vulnerabilities, you deter or make it more difficult to exploit it. Okay? And basically, ASLR, as its name says, address space layout randomization is about randomizing or make harder an attacker to know where my code is. So typically, the attacker needs to jump or to execute using rope, jump to leave, return to leave or whatever, need to know where my application is living, what directions are using. Okay. From now, we are going to suppose that ASLR is complete. I mean, everything is compiled with pi, means the executable is also randomized, and let's say full randomization is implemented, not partial or whatever. So we are going to things that can be randomized. I mean, there are many objects. There are many, in the sense, objects, blocks of memory, chunks of memory. We are not talking about object-oriented programming, nothing like that. So the heap, the stack, the program, the executable, the libraries. The maps that you allocate using mmap, files, anonymous, whatever. All that are objects. All of them must be randomized in order to be fully protected. Otherwise, the attacker can focus on one of them. Okay. So how works ASLR? We have, this is the typical memory layout that we can see in a textbook. The stack is on the top, the executable is bottom here, the heap, and in the middle, somewhere in the middle is the libraries and the mmap files. The heap can grow up, and typically the stack grows down, depending on the architecture, but it works that way. Okay, so if we have no ASLR, the attack is trivial. I mean, we can jump, we can redirect the flow. We are not talking about how to protect redirecting the flow. Okay, so the bug is already existing, and we don't care how it is managed or who it is done. ASLR is, let's suppose that the book allows an attacker to redirect the control flow of a program, where to jump. Okay, if there is no ASLR, it's trivial. We know where, because the attacker needs an absolute direction. But what happens when the ASLR is enabled? The libraries are shifted a little bit, a random amount of memory, so you don't know exactly where to jump. How much it is shifted is the entropy. Okay, is the amount of entropy that a given implementation has. Okay, and the effectiveness, the general effectiveness of the ASLR is how difficult is to predict the target, and how many vectors do we have. I mean, it depends not only on the number of bits of the entropy, but there are some other elements that interact. Also, let's say, it's important to see that there are other protection techniques, like a stack smashing protector or data not executable, that are really simple to understand, simple to implement, and very effective. Okay, they are great. I mean, in X means that you don't, or you write on a page of memory, or you execute it, but you can't do both. So it means that you can inject code, but you cannot execute. It's easy to implement, clean. ASLR is quite more complex. There are many factors. As we can see, there are many different objects. How those objects are randomized. What are the relation between them? When they are randomized. So it's a little bit more confusing. So be prepared a little bit, because this is not going to be trivial, and we are going to skip a few things, just to make this short. Okay, so let's go to the weaknesses. The first one is obvious. Okay, before entering, one idea. More or less is like, what is the background? Why these weaknesses exist? It's not for free. It's not because it's wrong. There are some reasoning about that. It's because typically the heap is a block of memory, is an object that typically can grow, okay? And the stack obviously grows downward. I mean, every time you call a function, every time you declare a local variable, the stack grows down, and then wind and unwind the stack, okay? So those two objects are typically considered to be growable objects. And so we have to make room for them. So we have to put the heap and the stack as far apart from each other, okay? So that is one question, and the other one is the fragmentation. We are in the virtual memory space, but if typically designers of ASLR want to leave a huge area of memory without nothing in the middle, so you can allocate huge blocks of memory. I can allocate, for example, a whole video file in a large area. Okay, so fragmentation and growable are maybe the problems. Okay, so let's focus on the first weakness, the obvious one, the amount of entropy. How much entropy bits have, in how many different places each object is located. Okay, we can see this is a very fast summary of the result. The main results is only Linux and PAX. We're going to focus on PAX because this guy has done a very nice work. I mean, as far as we know, it's the best implementation right now in Linux and many other places. But, so it's the implementation to beat. Okay, it's the best. Okay, so right now in Linux, in both cases, is quite weak. Meaning the number of seconds. Well, this is the executable, and this is the speed. It's considering 1,000 trials per second. This is the time needed to break Linux, 1 second in 32 bits, 32 seconds using PAX. This is the real entropy of the executable. This is not the real. There is a small bug in the PAX test tool which measures incorrectly. In fact, it measures the libraries and not the executable. Okay, so there is a small bug in the PAX text. And in 64 bits, in fact, it's strange, but Linux has more entropy than PAX has on the exec object. Okay, nothing more. Nothing more. More entropy bits, the better. That's all. And there are many restrictions about that. Okay, remember, the stack and the heap must be as far as apart, and I don't want to create fragmentation. The fragmentation problem is a big one. The next one, the second weakness. When we talk in computer science, when we think about random numbers, immediately we think about a uniform distribution. Nobody thinks about a normal or a triangular or any other, or logarithmic or Poisson. It's for statistic people. Okay, so we think in a uniform, a flat, something like that, with some noise. What about if we don't have a uniform? What about if the addresses of the ASLR are not equally distributed? Okay, initially it is not bad. Okay, for example, something like this means that this is not uniform because in the side we have a sharp drop almost close to 0. But there is a large area of randomness. Okay, this is a triangular. Okay, and here this is something different. An attacker can focus on this element, these values. Okay, this is this represents an histogram. So this is the probability of finding this address. This is normalized from 0 to 100. We will see later this value. We can see it. This is not good from the point of view of the defender. From the point of view of the attacker, this is fine. Okay, I will try to use these addresses. These addresses are more likely, much more likely than this one. So in fact, I will never use it. Okay, so do we see this in real implementation? The answer is yes. Libraries in the implementation of PAX in 32 bits follows exactly that, a triangular. And in 64 bits follows something like this. This is not a Gauss bell. It's called Irwin-Hall distribution. Why this happens? This happens because adding two random numbers of the same range gives a triangular. And adding three numbers of the same range gives this distribution. Okay, in both cases, it's not bad. I mean, there is entropy. Okay, that's good. It's very nice, but not as much as initially expect. In fact, in the triangular, you have one bit less. Okay, this is the way to compute. This is internally. The algorithm to calculate the address of the ASLR is using the sum of two random values of the same range, and in 64 bits, we don't see it, but it's the sum of three different of 2 to the power of 27. Okay, so okay. Next weakness. Let's see. Okay, next weakness: correlating between objects. Let's see. All the elements, we are not playing with one single executable or not executable. We're playing with entropy of different objects. What about if all the objects are put side by side, all together? If by any reason there is an info leak of one address belonging to one of the modules, then we know the position of the others. Okay? That is called correlation between objects. We call it that way. So knowing some information, having some information about one object, if it gives you a hint about where another one is placed, we call it correlation. Okay, Hector will show you an example of direct correlation, very fast, zero total absolute correlation, call it offset.lib. But and recently, 2 weeks ago, the people from NorthBit published the metaphor attack, which uses the correlation property. And Android, all the libraries are correlated, means all the libraries are loaded in memory side by side. So if you break the ASLR of one library, you can jump, you can exploit the bug on another. Okay? They used both this correlation and also in 32 bits the low entropy. So they make a small brute force against one library, which has special configuration, and once knows the direction of the library, then they jump to the target. Okay, and there are more interesting things about correlation. For example, this is more. If all the bits are put together, one side by side, knowing one, you immediately know the other. But there are other places that correlation can be useful. For example, when two objects A and B are correlated, and one object B has more entropy than A, and the conditional entropy of B, once you know A, is smaller than the absolute of B, then it's useful. Okay, so let's put some numbers because I'm going to skip this a little bit. So in Linux, okay, queue pages are randomized with this amount of entropy, 19 bits. Libraries use 28 bits. We are not going to enter because it's alignment. Queue pages has more aligned bits because of pages are larger. Okay, the entropy between those kind of objects are 9 bits. So if I try to attack, to guess, assuming that we have a vector to do that, the libraries, we have to make an effort of 2 to the point of 28, okay? 3 days. But if I attack, I brute force, first queue pages, if I can, and then knowing where the queue pages on that system are located, trying to jump, trying to guess, to know where the libraries are, the attack consists on breaking or brute forcing 2 to the point 19 plus 2 to the power of 9. We result in 8 minutes. Okay? So splitting the attack in 2 steps makes much faster, a lot faster. Okay? Queue pages today, I mean, it is basically, queue pages are used in databases and some scientific applications, but maybe in the future it is going to be used in a transparent way to load huge libraries or something like that. It depends on the configuration of the system. Okay, next. Next one, the inheritance. This is a form of correlation, but correlation between a father and a child process. So basically the idea is here we have a child process and this is another children. There are siblings. Let's suppose both processes are siblings. So we say that there is inheritance weakness if the position where a map will be placed in one child is the same or can be used to guess where will be the position of another map. So in other words, I am a child, and all my siblings, a child of a process, all my siblings, I can imagine what are going to be the future positions of the maps. So I can know the future layout of all my siblings. Okay, that is the typical behavior of fork, but it's how it works. Okay, and this affects, or it is interesting in applications or frameworks or architectures that use a lot of forking without exec. Okay, because exec renews all the secrets of the process, the canary, and the ASLR. So Android with Zigote, for example, has this kind of, let's say, weakness. Many launchers some launchers using in desktops. Chrome browser has also a similar concept about Zigote, and any process that uses the forking model, for example, Apache also uses the forking model, and so on. Okay, so it's what I said. You can predict the future of the layout of your siblings, and that's all. Okay, going faster, ASLR analyzer. We have developed a tool which, as I said, Paxtest is a nice tool. It was great, but has basically two bugs. I mean, the entropy is not computed in a nice way, let's say, and there are some bugs in the way it collects the addresses, okay? So, and we need a much more powerful tool. So we develop a tool with two elements. The sampler, which is, it collects a lot of data, a lot of addresses, a lot of information about the layout of a process, and the analyzer that computes several statistical parameters, individual, you're not going to see, okay, yeah, here. Statistical analysis, distribution plots, and several ways to measure entropy. Entropy is very difficult to manage, to understand, and to measure. Okay? A simple measure of entropy is not enough. Okay, so this is how it works. We can sample a system or many systems, and then the analyzer collects all the information, put all together, performs statistical analysis, and displays it in a view. Okay, this is what we will see. Okay, so it is possible to compare several systems, to compare the main stack of and all the information in the white paper, and we will show you is taking this tool. Okay, the tool gives two things. I think it's very important to understand and to play and to really make useful things. We need nice and easy to use tools and very graphical. Okay. There are a lot of information here. You cannot even imagine. I mean, here, well, yeah, you imagine or even see, because here says exec, heap. There are maps here. Okay. And here are, for example, an example of what are all the statistical parameters that are given by the tool, how much the distribution feels at uniform using the statistical McPherson-Chi goodness estimator, and several views of the same object, of the same data. The more information, the better. Okay, the mean, the mode, the standard deviation. 3 parameters for randomness. How many random bits we have? What is the Shannon entropy, as it is, the expression of the equation, and the sum of the Shannon entropy of individual bytes. And if we imagine more ways to measure entropy, the better. Okay, and the correlation. This is the typical correlation matrix, but we need something more powerful, which we are developing. We're still working on it, which is the coentropy. This is something, but it's not possible. It's not easy to measure in such a big space, because the address space is very huge. Okay, so that's all. Okay. I don't know. How much time do you have? 5 minutes? Okay, I can show you the tool. Yeah, it's nice to see, because it's so we can have it. I have been as fast as possible. 5 minutes. So let's wait a little bit. Firefox. and then TMP, whatever. Okay, now I will show you. No. Oh, yes. Bueno, ahora lo veremos. Okay. Index here. Index here. Okay, let's see if we can show you. Okay. So this is, for example, the output. The output is very handy in the sense that you can, I mean, for example, here it says information about what is the exact system where all this data has been collected, what is the version, and some information about page size, minimum address, as much information as we can. Let's go here, for example, and if we click, we can, well, I have to make it smaller. Okay, here, okay. So we can see it, and when we put over one of the maps, for example, main stack, we see nothing. Let's see. Okay, that's too much. It is going to be somebody here. Well, but this is 42 bits. Yeah, this one. So, like that. Okay. So we can see where each of the maps is located or all together. Okay. So we can see the layout. And this is, for example, in fact, which is the largest memory, the largest allocatable block that can be done in 32 bits. Because of fragmentation, this is normal, and so on. Okay, so here we have the detail of the, you see nothing, but, okay, wait. I don't know what is happening here. Let's see. Oh, it is, wait a little bit. No, yeah. Okay, so we can see the heap or the main stack or dynamic loader. Okay, here we can see the triangular that I showed you before is real data collected, or the map, some others. Okay, this is, for example, heap pages. It's interesting because heap pages, the entropy is so low, and some so low bits that there is even gaps. There are some addresses that it never happens. Okay, so we can see it. And then at the end, we have the, okay, nothing more, the entropy. So for example, in this case, we can see that the arguments and the main stack are correlated. The heap and the malloc, we collect, it is possible to collect as many objects as you can, and you can repeat or whatever. So you can make a very large and extensive analysis of many objects different. Okay, I will not show you. I mean, and this is all. And the way to collect it, well, it's not necessary. Okay. Hector will continue with the presentation.
Oops, what's okay? Hello, my name is Hector. So, as you can imagine, we can now detail we can now explain the 4 weaknesses in detail. But I'm going to show you how to exploit one of them, how to bypass the NX, the Stack Smashing Protector and ASLR in a 64-bit architecture in less than 1 second, exploiting one vulnerability we call offset to live. Okay, so this is an example of how to exploit one of the weaknesses Ismail had been present. So 1 second, I have. Okay. So as Ismail says, the problem appears when the executable is PyCompile, because the executable is loaded in memory side by side together with the libraries. So maybe you think that the ASLR is a mechanism which loads every object in every place of the memory. But actually, for instance, to randomize the libraries, only the first one is randomized. The other ones is loaded side by side to the first object, to the first library. Since the executable is PyCompile, the first object, shared object, is the executable. Which this means that the executable is together to the libraries. So if we are able to leak an address belonging to the executable, then we can directly, without any effort, obtain the addresses where the libraries are made in memory. So I will show you an example. If you execute in your system, because this vulnerability is already present in current systems, this was fixed in Linux 4.0, 4.1, I don't remember. The executable is in that direction, and the libraries are, as you can see, an offset, as I will show you in a second. Oh, sorry. Whoa. Sorry. I pressed the wrong button. So the distance between the executable and the library is constant, okay? The same to any other library, of course. So we name this invariant distance offset to lib, okay? Okay, just 1 second. So this is just, it's not a vulnerability exploitable by itself. It's more like information that the attacker can use to do attack faster or more reliable. Okay, it's not okay. I'm going to use this to bypass the ASLR in all systems. It's at the end it depends in a lot of things. But I'm going to show you the steps that an attacker need to do to exploit a correlation weakness, the offset to lib weakness, and bypass the three most protections. So the first step is extracting the stacked information. The second one is brute force part of the save IP, calculate. I'm going to detail these steps, okay, in order to go faster. So at the end, we need to obtain an address belonging to the application, okay, as I said before. So in this example, I'm going to exploit a stack buffer overflow, and then perform a brute force or obtain the address in the stack in order to use this address to use this address to calculate the offset where the libraries are mapped in memory. Okay, I will show you in a moment. So a lot is not see. Okay. So the point here is we have a vulnerable function. Okay, when we call this vulnerable function, we assume that this have a buffer overflow, like this. So when the buffer is overwritten, the return address on the stack is also overwritten. So we don't know what value put here, okay, because it's all randomized. But we know something. What we know? Okay, we know that the highest bits are always the same, okay? If you try to run an application in Linux, you can check that the highest 44 bits are the same, okay? The same happens in the lowest bits. From the ELF, you can obtain the lowest bits where the next instruction to the call to the vulnerable function is in the executable. So in this case, this bit can be directly put in the unknown address we are looking for, okay? So at the end, we have some information about the address. This is offline, okay? This is fast and offline. You don't need to do any attack to the server. You can obtain this information. So in order to obtain the remaining bytes or bits, we are going to perform a brute force attack against the save IP, the save IP address, so the address that is on the stack. So the first one is special because we already have the number 2 in this byte. So we only need to perform 60 attempts in order to guess what is the byte. The idea is that we are only to overwrite part of the return address on the stack. Only this part. Since we know this first byte, we can put one overwrite that put, for instance, 1, 2, DF. And if we got a crash, then we can try 2, 2. And if we got a crash, 3, 2, until we get the correct byte. Okay? So guess the second byte only costs 60 attempts in the worst case. Okay, we assume that is C2. Okay, we can put in our book C2. And the remaining 3 bytes, we can perform the same strategy, the same idea, perform another byte for byte attack. So, but instead of 60 attempts, we need to perform, in the worst case, 216. Okay? So this is not C, but at the end, we have obtained the remain bytes. Okay? And the number of attempts is only less than 1,000, is 768 bits attempts. Sorry. Well, okay. So once we have the address on the stack, we need to know where the executable is in memory, because this address is not the base of the executable. Okay. So we can calculate. Here we need a symbol in order to do the correct operation. This is a mistake. So the application base can be calculated as I show you here. The only trick here that even I show, maybe you know the blind attack, use a similar strategy that us, but I think they forget to adjust the text base area. So we need to know the offset from the executable where the call is made in order to adjust the application base in memory. Okay, maybe it's a little bit tricky. I'm going faster. So doing this operation, we obtain in the left where the executable is in memory. So once we know where the executable is in memory, just doing a simple operation, we can obtain where the libraries are in memory, and then we can build rope attacks or whatever we want. So we have here some pre-calculated offsets depending on the system. So you can do this offline, basically. So this is the example I told you. The list is doing this simple operation. Subtract the offset to lib to the text base address. So to show you a more realistic proof of concept, this is our system. This is the system we are going to face. So we are going to bypass the non-executable bit, the stack machine protector, the address spell randomization, the fortify, the railroad. Also, it's worth to mention that we don't use Go, PLTs, and I run this in my current laptop, so it's full updated today. This morning, I update my laptop today. So, and the demo is the following. I'm going to show you. So, this is the server, which have a stack buffer overflow, a typical stack buffer overflow. Okay, it's compiled with the maximum protections. I'm going to show you quickly. Pi protector. Okay, -2. Maybe this is anyway. So the server is running in this port, and we are going to launch the. 1 second. Anyway. Okay, the exploit wants a server and a port. So since I am in localhost, I will put localhost and the port 999. And this is going to perform a brute force attack against the return address on the stack, and then calculate all the steps I showed you, and then build a rope, and then got a shell. Okay? This is a 64-bit machine, okay, with all protections. So oh, sorry. I have to. There are a protection mechanism. Well, it's not a protection. Actually, it's a crash reporter in Ubuntu by default that every single process, every time that a process crashes, they write a report on the disk. So my laptop is not very fast. So right now, they are rating these reports, which consume a lot of time. But I'm going to disable 1 second. It's not a security mechanism, okay? Okay, I stopped the crash report generation. And as you can see in the other window, okay, I don't know where is it. There are a lot of stack smashing detected, but anyway. So I launch again the exploit, and now I expect, yeah, okay, more or less 1 second we got a shell, as you can see here, a root shell. So we are bypassing the three most known protection mechanism, okay? This is just to show you what or how dangerous can be a correlation weakness, okay? So, 1 second. So to solve this weakness, we can use directly pass because packs already put the executable apart from the libraries. It's not in the same area. So this vulnerability does not affect packs. Also, we send a patch to the Linux kernel. So for versions greater than 4.1 is also not a problem. And there are a specific protection for stack buffer overflows called, which the name is Renew Stack Smashing Protector. This is a particular solution for stack buffer overflows, which prevents brute force attacks against the stack smashing protector. Okay, so the solution in the kernel 4.1, we have the executable in the same more or less addresses that the libraries. And with the patch, the executable is in different ones. So if you guess an address here, you cannot use this address to obtain where the library is in memory. So the patch is as simple as that. So we're going to present also the address space layer randomization next generation, with, of course, avoid this weakness and the other 4 ones presented by Ismael. But it's worth to mention quickly how we solve this correlation problem. As I said before, I'm going faster because I say already. The problem is that the executable are joined to the library. So just by moving the executable far away from the libraries, the problem is solved. Okay? So this attack was rewarded by packet storm. We sent a patch to the Linux kernel. Okay. But what about the other weaknesses? It is possible to remove all the other weaknesses, because it seems that it's quite difficult, because the heap cannot be put in the top or the stack at the bottom. Otherwise, the stack cannot grow as much as they want. And the weaknesses appear because of that, because of the limitations. So the idea is that if we can bound growable objects, we are able to move these objects around the full virtual memory space. Okay? Instead of allow the stack grows, we can bound the stack. So if we have not growable areas, then we can move the objects anywhere in the virtual memory space. This provides us a huge increment of entropy. And also, because we have no restrictions, or because we have no calculate some addresses using other addresses. For instance, the executable is in a random location, but the heap is calculated using where the executable is in memory and adding another random value. So when you start to do these kind of things, then start to appear problems, like correlation ones. So doing this simple idea, I explain why this is not as simple, we can have a lot of advantages and then prevent the 4 weaknesses, okay? No more likely addresses, no more correlated attacks, and even do a more secure forking model, okay? This is a summary of our work in the new ASLR that we are going to present here. We are presenting here. Basically, we introduce new features like the possibility to map a specific request in a random place using the full virtual memory space. Okay, right now, if you want to map some file or whatever, you need to call to a map, and Linux will return you an address joined to other objects, joined to the other libraries. So we introduce a new flag to a map system call in order to put this concrete object in a random place using the full virtual memory. Okay, but not only this. There are a lot of new features. We have no time to explain all of them here. But for example, we have improved how the heap works in Linux, or we have improved the mmap system call. We have introduced the ability to randomize parts of the address at both time. We call this bit slicing. This is similar to per boot randomization. Okay, we fix an EMD bug using this randomization. Okay, maybe, okay. And it's not, you cannot see here because it's cut, but we introduced the idea of isolate similar objects in similar regions of memory. So why thread stacks, for instance, need to be in the same area than libraries? So it is possible to detect this in the kernel in order to put these stacks together in another place in order to avoid correlation attacks. In other words, if you obtain a leak or an address belonging to a thread stack, in current implementations, impacts in almost all cases, but in Linux in all cases, you can use this address to the randomized libraries. So why don't put the stacks in another place? Why don't put all stacks in the same area? So all of these randomization forms that we have introduced produce a lot of maybe too much configurable options. So we decided to create 4 profiles modes in order to do the ASLR NG more usable. So the first one is the concentrated, which try to put all objects together. Okay, this is the most correlated one. This obviously you can use the correlation weakness to attack any object because all are together. But the point here is that you are saving a lot of page table size memory, and you are not losing entropy, absolute entropy. Okay, from the outside, the attacker can know if the executable is in the top or is in the bottom. The executable can move free along the full virtual memory, which provides a lot of entropy, a lot of absolute entropy. So the conservative is more similar to Linux. They try to put the stack in their own area, and the executable and the heap also, and the other objects together in the same area. Okay, this is to try to save page table size and to be the more compatible possible with current Linux. So we create the extend mode, which, for instance, put all the thread stacks together in order to avoid correlation attacks between stacks and libraries, or attacks stack in executable. Okay? And the paranoid mode, which basically is the more secure, but is the more page table size consuming, because all objects are isolated each other. So there is no correlation between any object. So this solved the correlation weakness. But there is a problem. If you use, for instance, the paranoid mode, there are a lot of page type size consuming. So, and another problem is, it is possible to map a big block of memory. And the answer here is no, because the object is using random positions, and you cannot guarantee a large block of memory. To solve this problem, we have solved the fragmentation issue, that is fragmentation, by pre-reserving half of the virtual memory layout. So if you pre-reserve half of the virtual memory layout and force that all objects are loaded randomly in the top, for instance, then you can guarantee large blocks, large consecutive free blocks of memory. Okay? The pre-reserved area is not always in the bottom. It's randomly in the top or in the bottom, in order to not lose entropy. It's a bit hard to explain here, but we are not losing any byte of entropy using this mechanism to solve the fragmentation. So comparing the fragmentation, as we can see, Linux provides almost 2 gigabytes of free consecutive space. PAX is half, more or less half, of the Linux. And ASLR-NG, our proposal, is half of the virtual memory layout. So I think compatibility is important. So the only thing that is not very good from PAX, I think, is that they can allocate large blocks. For instance, you cannot open up, or you cannot map a video of 1 gigabyte, for instance. You will get an error because you have not 1 gigabyte free, or you have any block of 1 gigabyte free. Okay, so the fragmentation is important, and I think that can be an issue. So comparing both the entropy, so here we have the ASLR-NG, our proposal. So these numbers are the same independently of the profile mode, because this is absolute entropy. So we can say that in Linux is almost useless because the low entropy. We can say also that PAX is better than Linux, but not too much, because for instance, the executable have only 15 bits, which can be brute force in 5 minutes. Okay? So using ASLR-NG around 2 hours to do the same attack. Okay? And in 64-bit architectures, obviously in 64-bit architecture, we have a lot of entropy. So the only thing that we found thanks to the tool developed for us is that the executable in PAX have half entropy than Linux. We don't know exactly why, but seeing the code, it seems that they use only 27 bits of entropy. So if the goal is to guess where the executable is in memory in a Linux 64-bit architecture, then Linux is more secure than PAX. But, okay. And even PAX have half bit more than entropy in libraries. We can say that because the non-uniform correlation, because the non-uniform weakness, they have less than 28.5 bits of entropy. So at the end, it's quite similar to Linux. Okay, but if you are focused in the executable, then Linux is better than PAX, twice. So concluding, we have presented 4 exploitable weaknesses, which increase the probability of success for the attackers that want to bypass the ASLR. We have developed a tool to measure the effectiveness of the ASLR, and thanks to that, we have found things like PAX in 32 bits is better than Linux, or that the executable is better randomized in Linux than in PAX, or that Linux provides a larger consecutive free space than PAX, which is very important for the compatibility. So also I saw a proof of concept of the correlation attack, or a correlation weakness, sorry, the offset to lib. And we also have contributed to the Linux ASLR by several CVS and other fixes. We found, for instance, a book on integer overflow in how the stack is randomized. And this is March 20, this is very recent. Maybe all of you know that by setting the stack to unlimited value in 32-bit architectures, you can disable the ASLR, and then it's easier to attack, for instance, say 2ED executables. So thanks to our patch, this is not longer possible. So we have designed and implement a new ASLR, which is compatible and effective, and address all the weaknesses we have described here. With the main features is that it is able to use the full virtual memory area to randomize objects. It's not limited. The stack is not in the top. The heap is not in the bottom. Okay. But to be usable, we have to solve the fragmentation doing the pre-reserved area. And we introduce the concept of allocate sensitive objects of the same sensitivity in the same area, isolated from other objects. Also, new randomization forms like be able to randomize specific maps. It's worth to mention that Chrome use also own ASLR to map JIT areas because they know that and they decide to put some areas in another place. So thanks to these new randomization forms, Chrome, for instance, could use it in order to remove all code to implement their own ASLR. Okay, and that's all. ASLR removes the for identity winning side, providing both maximum entropy without fragmentation issues. This is the most important. Okay. And as a final conclusion, I can say that ASLR-NG overcomes Linux and PAX in all aspects. And that's all. Questions? Yes. Yeah, it's a sum. Because it's a, yes, I can show you quickly. Yeah, it's normal. Okay, 1 second. This one, okay? So the idea here is, if you perform an overflow and you don't touch the return address, the program will return to its color perfectly. So you don't observe any correct behavior from the server, okay? But if you start to overwrite only the first byte, how many possibilities do you have per byte? So when you guess this byte, then you can use it to perform the brute force attack of the second byte. And you have also 256 possibilities. Okay, because when you overwrite the correct one, you will get a normal answer. Otherwise, you will crash. So you have an oracle. If you put the correct address here, you will get a correct answer from the server. If you put a wrong byte here, you will get no answer because the child will crash.
So the address is already, the address was the correct. Imagine that you have the right address to jump exactly to the return position that the program wants. So you can overwrite one byte, and the rest of the direction is correct, it's perfect, because it was there. So you overwrite only one. If you overwrite with the right value, you return exactly to the correct function, which is the one that the program wants. Okay?
Yeah, we have symbols here, but actually the address is on the stack. It's correct. This is for the attacker. They don't know, but the application already know. Okay?
You put exactly the same address that was already in the memory.
Yeah.
So every time your guess is correct, means that you have overwritten something which was already there, but you know now.
Yeah. Sorry?
Yes, it's one byte independently by one byte, randomly guess. So 256, one I know is very byte, I can go to the second one plus 256 plus 200. It's not a multiplication, it's an addition.
Yeah, but you need to be able to hand byte level of overflow. Otherwise, if you only can write words, you cannot perform this attack. You need to be able to overwrite a byte level, okay? And the last overflow is the complete address. So the last overflow is, okay, I'm going to put this address in order to see if I got the correct answer from the server. So you are sure that you have put the correct address. Yeah, if it can be done remotely. Yeah, of course. Yes. Yeah, you have, yeah. For example, in the ASLR, we propose if the bug exists in a thread stack, for instance, in the stack of the thread, sorry, instead of the main stack, assuming that this buffer is in the thread stack, since the thread stack is requested by the mmap, if each time a new child is created, you use the ASLR in order to randomize where this stack is going to be in memory, this can be more difficult. Yeah, that's absolutely, yeah.
Yeah, for example, the SSH suite uses the trick, well, the bad thing is right after a fork, always execute an exec. So even direct child execute fork plus exec in order to re-randomize everything, libraries executable, the canary word. So it's very safe, but very time consuming. There shall be a balance. Forking model is very useful in embedded systems because of the speed. So Android uses forking model for that. And there's a bit.
So they're using I'm not sure to answer your question. Is the vulnerability, what?
I don't think so, because this is general, I mean, how function calls works. So this call return, and then this is the address stored in the stack, the return function, the return address. So it's very generic. It doesn't depend on a compiler or an operating system. It's not a trick of Windows, probably will be half exactly the same.
But you're asking about how to prevent this. Maybe there are techniques like control flow integrity that they are developing in ELEVM and these kind of things. But also, we are able to guess this address. What is doing the control flow integrity is preventing that we can redirect the flow. But yes, at the end, this is prevented with the control flow integrity. Okay. Yes.